Okay, on to problem 3. This is a nasty looking molecule, but it's similar, comes about because we've learned about aromatic chemistry, we learned a lot about enolate chemistry, and we're seeing some things we can do. Now, this one's a little more complicated. Our carbon sources, benzene and any hydrocarbon or anything with CNX and O, CH and O with N less than or equal to 4. So basically, we're limiting ourselves to 4-membered rings. I forgot to mention that you could use an amine in here too. Now, this is our carbon sources, so we can use anything else, but these are the things that have to show up in the molecule. So let's go ahead and do our retrosynthetic analysis. So I look at this molecule and I can see, okay, there's different ways I can make it, but one of the things I want to do is think about this methyl group and this group. We can make that through some enolate chemistry on this compound. So now we have to concentrate on making this, and how can we make this? Again, I'm going to use this strategy of making a nucleophilic carbon. So we need to make this. We'll turn it into the Grignard. We can have nucleophilic carbon. We can do a conjugate addition. We have to be a little tricky to make sure that goes in the conjugate position, because Grignards actually prefer to do normal addition, but we can take care of that. And each of these can be made from these compounds. So let's go ahead and start from the beginning. So we can make this 6-membered ring by just taking this alpha-beta unsaturated aldehyde and acetone. We could have thought about using the ketone and then benzaldehyde, but benzaldehyde is too good an electrophile, and we'd get a lot of aldol product in that fashion. This is not as good of an electrophile, so we're much more likely to get less electrophilic chemistry happening at this carbon, and we can get our conjugate addition. We are going to get a little bit more of the normal addition just because of the access of that aldehyde, but this will probably give us the highest yield of the 1,5-dicarbonyl compound, which can then undergo an intramolecular cyclization to give us our 6-membered ring with the alpha-beta unsaturated, because we want to do a conjugate addition there. To make our aromatic compound, we just have to go ahead and install the ethyl group. Then we can do a bromination and we can get the para. We're going to have a little bit of ortho there, but these would be easy enough to separate. We're probably going to get a higher yield of the para position just because it's not horribly sterically hindered, but it's an ethyl group, so we're going to get a little bit better chemistry at the para position. We can separate it, clean it up, and then do a nitration. This is going to go, again, we're going to get a lot more at this because this will be the more active carbon, because this is a better activator group. This is actually not that great of an activating group, so we should get a high yield of our product with the nitro group in the right position. So once we've done that, we can just go on and do our next step. We just have to clip these things together. So we're going to make this into the Grignard. We don't have to worry about protecting anything. We can make this Grignard. It's going to be a reactive Grignard. We want the conjugate addition. We talked a little bit about this in class, but I did tell you that for you folks, you can always assume it's going to be conjugate addition. If we didn't put the manganese chloride and the copper chloride in here, we would get a lot more of the normal addition. This is some tricky chemistry that seems to activate the conjugate addition, and we get high yields of the conjugate addition, and we get that here. So now all we have to do is finish this off by doing the last step where we're going to install these two positions. Now, we could do it in either order, but we'll get a higher yield. The first reaction we're going to do is simply the methylation reaction. This will go in high yield. Doesn't matter which side it goes on. It's going to be the same side. So we can get a high yield of the monomethylated product. Just by using the stoichiometry, we used LDA. We did it at low temperature, and we add methyl iodide to that. The next step in the reaction, we're going to use morpholine to make this enamine. Morpholine has a few advantages. We could have also used something like pyrrolidine, But morpholine will make this slightly less nucleophilic, and that will help us to undergo the next reaction. If we had a more nucleophilic enamine, we might get a little bit too much chemistry happening at the carbonyl compound. This will help get us the reactivity at the correct position, the SN2 type of position here. So we end up with our final product. And we just have to work it up under acidic conditions to get rid of the enamine. And there we go. We're all done.